Okay, today we are going to start a new chapter on project scheduling. Okay, this is not a totally new topic for you, okay, because you would have touched, okay, a little bit on project scheduling during your first year when you are looking at operations management. Okay, so a bit of this is recap, a bit, maybe a little bit of new knowledge, but project scheduling is definitely, okay, one of the common tool, okay, that is used in decision making. So in this particular topic today, we are going to touch on 3 subtopics. Okay, 1, project scheduling based on expected activity time. Okay, that means we have an idea how long a particular activity is going to do. Okay, and with that, we try to schedule out, okay, our project. Or we could also look at project scheduling, okay, based on uncertain activity time. So if the timing for a particular activity is not quite certain, we use a different method, okay, to actually calculate the schedule for that particular project. And finally, we look at considering time cost trade-off. Okay. In project management, okay, PERT, okay, program evaluation and review techniques, as well as CPM, critical path method, are 2 extremely valuable techniques, okay, that is commonly used to plan, to schedule, as well as, okay, to control the progress of a particular project. So in many projects, okay, the role of the project managers is that they must schedule and coordinate, okay, different activities, okay, or different jobs so that, okay, the entire project can be completed on time. So the PERT and CPM generally have the same purpose, okay, and uses mainly very similar terminology, okay. However, both of these techniques, okay, are developed or were developed independently. Okay, PERT was developed back in the 1950s, if I'm not wrong, okay, by the US Navy for the Polaris missile project. Okay, many of the activities that happened in the missile project, okay, at that time has never been attempted before. So the PERT was actually developed to handle uncertain activity times related to this particular project and has since been used. Okay, the critical path method, on the other hand, were developed, okay, by DuPont and Remington Rand. Okay, primarily for industrial projects where generally the activity times are known and variability of the activity times was actually not such a big concern as compared to the missile project. So some of the activities or some of the projects, okay, that commonly use PERT or CPM is when we have an R&D, okay, for new products and processes. Okay, if you have a construction job, okay, of buildings, highways, if you have maintenance of large complex equipments, design and installation of new systems. So these are just some example of people or areas that actually uses the PERT or CPM to actually plan, schedule, and control their projects. So in these types of projects, okay, project managers must schedule and coordinate the various activities. So projects may comprise as many as several thousand activities, okay, and a complicating factor in carrying out these tasks is the interdependencies, okay, of some of these activities. So for example, okay, some activities depend on the completion of other activities before they can be started. Okay, something that I hope you can also remember. So the PERT or CPM, okay? Many project managers actually uses the PERT or CPM to actually help them answer some of these type of questions. Okay, so if you have a project, you plan out, you want to know what is the total time, okay, that is needed to complete the project. What are the scheduled start and finish date for a particular activity? Which activities are critical? Okay, which are not? If they are critical, then they must be completed exactly as scheduled so that the project can be completed within the stipulated time. Okay, and how long can non-critical activities be delayed before they cause an increase in the project completion time? Okay, let's go to the first one. Okay, the first one is on the project scheduling based on expected activity time. Okay, a quick recall. Okay, if we have a project scheduling, we draw up a project network. Okay, what is a project network called? There are two types of project network. Okay, can you all remember what are they? Okay, we have a project network. Okay, where the activity is on the node itself. That is called the okay, we have got, give me a minute, my pen is not working again. Okay, we have got activity, and we also have another type of network. Okay, what is this first one called? What type of network is the first one? Can you all still remember? Oh, anybody home? Forget already. Adoy. Chien, forget the rest. I think I need to mark attendance for Chien only. The rest of you, I can just delete off your attendance because there's no one in class. This is the AON network and this is the AOA network. Okay, activity or node. Okay, where the activity is inside the node, represented by the node, and AOA, activity on arrow, where the activity is on the arrow itself. Okay, so in this particular topic, okay, we are going to use the AON method, okay, where the activity is on the node itself. So here the nodes, okay, represent the activities. Okay, the arcs, so which is the arrow here. Okay, in this particular book, it uses the word arcs. Okay, or you can use the word arrows. Okay, so the arcs reflect the precedence relationships. Okay, and then the critical path of a network is a path consisting of activities with zero slack. So let's look at an example. Okay, this is to jog your memory. Okay, you will have known most of this. Okay, so here we have an example of the Western Hills Shopping Center. They want to build, they plan to modernize and expand the current 32 business shopping center complex. Okay, the project is expected to provide room for 8 to 10 new businesses. Financing has been arranged through a private investor. All that remains is for the owner of the shopping center to plan, schedule, and complete the expansion project. So here, Okay, this is the list of the activity description, the immediate predecessors, as well as the expected activity time. Okay, can you all still remember how to draw this? Okay, so here, and this is, okay, each time each time you do this, it's slightly different because different textbooks or different ways of using it. So here, okay, what I want you all to do is you will always have a start and finish node. Okay, you always have to have a start as well as a finish node. Okay, activity A has no predecessor, so you will have A. Activity B has no predecessor, you will have B, and they then come from the start. Okay, so that, okay, you will know that activity A and B, okay, are the first activities to start with. Okay, and then the last activity here is activity I. So when you have the last activity I, and that is the completion, then you will then, okay, create an arc between I and finish to indicate that I is the last activity and you are finishing off your projects. Okay, immediate predecessors identifies the activities that must be completed immediately prior to the start of that particular activity. So we have A and B. Activity C comes from activity A. So we have A goes to C. D also A. So we have D. And then E also have a predecessor of A. So this is C, D, and E. Activity F, obtain approval for building permits. Immediate predecessor is E, so here is F. Okay, activity G, predecessor is D and F. Okay, so here this is too soon. So D and F, G. Activity H, predecessor is B and C. So we have B and C. H is B and C. I'm just trying to see how I can draw this. Okay, I'm going to put down activity C here, and then B here. B and C go to H, and then we have I and finish. Okay, so this is a sketch of the project network, which you can find here. So this is the graphical representation of the network. This is your AON.
Hi, doctor. Can I ask a question?
Sure.
In the diagram, we can change the change the sequence, right? Right. C can at the bottom, no need at the top. So we
Correct.
can go. Oh, okay. Okay, thank you, doctor.
You can change, like you don't have to have C on top. Okay, in an AON, what we try, okay, why did I change C down? Okay, if I put C on top, then I would have to crisscross. Okay, that is something that we want to avoid. So let's say, right, if I put C on top here and B at the bottom, so I will then need to crisscross over other activities or crisscross over other errors and over other arrows, and that is something that we want to try to avoid. Okay, so it doesn't have to be C, D, E. It can be in any sequence as long as we try to avoid, okay, having to have one arrow going this way and then another arrow crossing like that. Okay, this is something that we want to try and avoid. Okay, so this is your graphical representation of the Western Hills Shopping Center project. Okay, so now that we have this particular project, okay, this particular project has a few paths. So what is a path? A path is any sequence that can lead you from the start node all the way to the finish node. Okay, so here if I start from start, so A, E, wait, start A, E, F, G, I to finish. So that is one path. Okay, another path will be from the start to A, to D, to G, to I, and to finish. That is another path. Okay, another path could be from A to C, to H, to I, to finish. Okay, and another path is from A as start to B, to H, to I, and to finish. So in this particular network, there are altogether 4 paths. Okay, 4 different paths that can take you from the start to the finish. So all paths in the network must be traversed. You must go through all these paths. Okay, in order to complete your project. But all the 4 different paths could potentially have different time of completion. Okay, and out of all these 4, the path with the longest duration, longest path, okay, determine the total time required to complete the project. Okay, let's say if path 1 takes, what is this? This is expected activity time. Okay, it doesn't tell me what it is, so let's say weeks. Okay, if path 1 takes 10 weeks, path 2 takes 15 weeks, path 3 takes 18 weeks, and path 4 takes 15 weeks. Okay, if that is the case, then the longest path, which is the path with the, okay, longest time to complete, which is your P3 here, okay, this is what we call your critical path. Okay, the longest path is your critical path. And activities on this critical path cannot be delayed. Okay, if they are delayed, your project, okay, will be delayed. However, on all the activities on this critical path is called the critical activities. Okay, so you have to be very careful to monitor, okay, and to make sure that all activities on the critical path must be completed with the stipulated time in order for you to ensure you can complete the project in time. Okay, in order to know, okay, what is the total time that is required to complete the project, okay, you will have to go through, okay, you will have to fill in all the time into the project network. And to do that, okay, you will need to do 2 different paths. You need to do a forward pass. And you will also, then after that, you will do a backward pass. Okay, just by doing the forward pass, you will be able, okay, to get the total time required for you to complete the project. However, you will not be able to know which one or which path is critical until you complete the backward pass. Okay, in this particular textbook, okay, the way that they actually represent the time is they used a square box. Okay, where they put the activity here and the time required for the activity, okay, right under the activity name. Okay, as we know, in the forward pass, okay, you will be able to identify the early start and early finish of the activity. Okay, this is in the forward pass. And in the backward pass, you will be able to then identify the late start and late finish. This is in the backward pass. I am flexible, okay, whether you want to use the format given here where you use a square, or if you want to continue using the format that you have learned. I think in OM, you might have used this way, right? This is the activity. This is early start, early finish, late start, late finish. Okay, I'm flexible. You can use either way as long as the answer is there. I'm happy whether you want to use the round note or you want to use a square note. Okay, it's all up to you how you want to represent your network. Okay, so I'm going to go through the forward pass and backward pass very quickly. So in the forward pass, you know that activity A has 5. So since it comes from the start, so the early start date is 0. Okay, so 0 plus 5 is 5 because this is the time. This is your activity time. Okay, activity B also start from 0. So this is 0 and it takes 6 time units. So this is 6. Activity E, D, and C can only start when activity A has completed. So the earliest time that they can start is at the end of activity A, which is 5, 5, and 5. Activity E requires 1 time unit, so 5 plus 1 is 6. Okay, activity F can start after E has finished, so this is 6. It takes 4 time units, so 6 plus 4 is 10. Okay, activity F then goes to activity G, but activity G can only start, activity G has 2 precedent activity, which is D and F. Okay, so let's wait for that. Let's look at activity D. Activity D, okay, starts at week. Let's say, okay, I'm just going to make it easy and let's say this is in weeks. Okay, activity D starts at week 5. It takes 3 weeks to complete, so it completes with week 8. Okay, activity G can start only after, okay, activity D and activity F have finished. Okay, activity F finish at 10, activity D finishes in week 8. So when can activity G starts? What week can activity G starts? Okay, yeah, activity G. How many of you are actually here in class? Or are you all just turning this on? Okay. So in the forward pass, activity G can only start after activity D and F has finished. Activity D finishes in week 8. Okay, however, activity F only finishes in week 10. So we have to wait until both activities have completed. So that means we have to wait until activity F has also finished. So G only can start after both activities has completed. Okay, it takes 14 weeks. So 10 plus 14, this is 24. Okay, let's look at activity C. Activity C, okay, starts at week 5. It takes 4 weeks to finish. So 5 plus 4, this is 9. Activity H then can only start when activity C has finished. So this can only start at 9. 9 plus 12 is 21. Okay. So now, activity I. When is the earliest activity I can start? Okay, precedent activity. So I, precedent activity is G, which finish at week 24, and activity H that finish at week 21. So when can activity I start? Okay, activity I can only start after both has completed. So that is in week 24. Okay, activity I. Okay, activity I takes 2 weeks. So 24 plus 2. So this is 26. Okay, so here we can see that this particular project, okay, will be completed within 26 weeks. Okay, by week 26, it will be completed. Okay, but we want to find out, okay, which activity is critical and which activity is not critical. In order to find that, we then need to conduct our backward pass. Okay, we know from the forward pass that this particular project requires 26 weeks to complete. Okay, so our latest finish starts with 26 weeks. Okay, and now in the backward pass, we will have our late finish. This is our late finish. And now we want to find what is the time for our early finish, which is our late finish minus our activity time. Okay, our activity time. So late finish, you have to finish in week 22. The activity takes 2 weeks. So this is 26 minus 2, so this is 24. So in the backward pass, you will then write the late finish of all the precedent activity. Okay, let's go with activity H first. Activity H needs 9 weeks. Sorry, activity H requires 12 weeks. So 24 minus 12, this will give you 12. Okay, so what comes in the precedent activity is C and B. So since H early start is 12, so the late finish here will be 12 and 12. Sorry, this is not early finish. Sorry, this is late start. Okay, activity B requires 6 weeks. So 12 minus 6, this is 6. Activity C requires 4 weeks. So 12 minus 4, this is 8. Okay, let's look at activity G now. Activity G, latest finish is 24 weeks. It requires 14 weeks. So the late start is 24 minus 14. So this is 10. Okay, that means the latest time it has to finish, it has to start is 10 weeks. Okay, so the precedent activities also has to finish latest by week 10 so that activity G can proceed. So here is 10, here is 10. So let's look at activity F first. Activity F requires 4 weeks, so 10 minus 4 is 6. So activity E is the precedent, so this is 6. Time required is 1, so 6 minus 1 is 5. Okay, let's look at activity D. Activity D, late finish is 10. Activity time is 3, so 10 minus 3 is 7. So let's look at activity A. What is the latest start of activity A? Latest finish of activity A. So we need to look at all the following activities, which we have activity E, D, and C. So in this particular case, we have to take the minimum out of all the following activities. So we have 5, we have 7, and we have 8. So in that's the case, then the latest finish time of activity A is 5. So 5 minus 5, this is 0. Okay, so now we have the forward pass and the backward pass. So we can identify now what is the early start, early finish, late start, and late finish of all the activities within our network. So in order to identify what are the critical activity and the critical path, we then need to calculate what we call slack. Okay, slack is early finish minus early start or late finish minus late start. That is the value of slack. So activity A, early finish minus late start, that will be your activity time. So it will be late finish minus early finish or late start minus early start. Okay, So it will be this minus this or this minus this. So 0 minus 0 or 5 minus 0 will give you a slack of 0. Activity E, 0. Activity F, the slack is also 0. Activity D, the slack is 7 minus 5 is 2. 10 minus 8 is also 2. So slack here is 0. Slack of activity C, 8 minus 5 is 3. Slack of activity H, 12 minus 9 is 3. Slack of activity I, 24 minus 24 equals to 0. Slack of activity B, 6 minus 0 equals to 6. So now, which activities have 0 slack? Okay, activities that doesn't have any slack are critical activities. That means they cannot be delayed. They don't have extra time for you to delay them. Okay, once these activities are delayed, then they will change, okay, the total time required to complete the project. So if we look here, so activity here, this one has 0 slack, this has 0 slack, 0 slack, 0 slack, and 0 slack. Hence, a path, okay, that connects the critical activities are your critical path. So this is from start to A to E, E to F, F to G, G to I to finish. So, hence your critical path is A, E, F, G, and I. So this is your critical path. Okay, any questions so far? Okay. So if none have, okay, good. We will have done all of this. Okay, we have looked at latest start time and finish. We have completed the whole network. We have looked at slack. Okay, we have identified our critical path. Okay, so once you have done that, then you have completed the project network. Okay, you can also put the information into a table form. Okay, by writing down what is the early start, the earliest start, latest start, earliest finish, latest finish, slack, and whether it's on the critical path or not. Okay, you can also compile all the information into a tabular form. So now, once you have done that, then you will be able to answer the question. How long will the project take to complete? So we know from this project network, okay, the time that it needs to complete the project can be found here, the last time here. So that is 26 weeks. Okay, it can be completed in 26 weeks. What are the scheduled start and completion times for each of these activities? Remember, these are the questions, okay, that we said right at the very beginning that PERT or CPM can use to answer them. So here, going through all these 4 questions. So by going through, okay, the forward pass and the backward pass, you will then be able to find out the earliest start date, latest start, earliest finish, and latest finish time for each of the activities. Okay, it's all here clearly shown in this particular network diagram as well as in this particular table. Which activities are critical and must be completed exactly as scheduled to keep the project on schedule? So we know just now, okay, that activity A, E, F, G, and I are critical activities Okay, and why are they critical? Because they don't have any slack. So we have identified A, E, F, G, and I as the critical activities. How long can non-critical activities be delayed before they cause an increase in the completion time for the particular project? So in this particular case, if I were to go and look at this project network, okay, let's say activity D. Okay, I'm going to look at activity D here. Activity D early start is week 5 and the latest start date is week 7. That means activity D can start either in week 5 or can start in week 6 or it can start in week 7. Okay, so activity D can start either week 5 or week 6 or week 7. So this is the early start and this is the late start. As long as activities start within these 3 weeks, the project, okay, the project will finish on time. However, if project D, for some various reasons, machine problem or whatever it is, start in week 8 or week 9, and so on, it will then delay the project. Okay, it will then delay the whole project, the schedule of the project. So how long can non-critical activities be delayed? Okay, so depending on the project, so activity D can be delayed for 2 weeks. Okay, from week 5, from the early start date, it can be delayed for 2 weeks because there is a slack. So S equals to 2 here, so it shows that it can be delayed for 2 weeks. Activity B, for example, now, activity B, the slack is 6. So just 6 minus 0 or 12 minus 6 is 6 weeks. So that means activity B can be delayed from 6 weeks from the date of the early start. And that particular activity, okay, if it's delayed for 6 weeks from the early start date, the whole project will still complete on time. Okay, so that's what, okay, project scheduling based on expected activity time, okay, can answer for you. And here I'm just giving you a summary, okay, of the critical path procedure. So first, okay, we have a list of activities. We have determined the predecessors and have estimated the completion time for each activity. Okay, if you don't already have that, then as a project manager, okay, you will need to compile all of these 3 information into a table. Okay, so here in this case, a lot of the time, these are given to you. What is the activity? What are the predecessor? And what is the time? Okay, usually here in exercises and in activity, in questions, okay, this table will be given to you with the activity, the predecessor activities as well as the time, right? However, okay, if you have to develop it on your own, then this is the 3 steps that you need to go through first. Okay, and only from here, then you can draw up a project network, okay, based on the information that you have in step 1, 2, and 3. And then from there, you then do the forward pass, okay, in order to determine the early start and early finish. And then do the backward pass in order to identify the latest start and the latest finish time for each of these activities. Okay, once you have completed the forward pass and the backward pass, then you identify the slack for each of these activities. And from there, okay, any activities that have 0 slack time are your critical activities, and the path, okay, that connects all the critical activities is or are your critical path. Okay, there could potentially be 2 critical paths or more. Okay, depending on the size of your particular project. Okay, so that is the first subtopic, okay, on project scheduling based on expected activity time, where the time is given to you. A fixed time is given to you. So another way, okay, is project scheduling based on uncertain activity time. Okay, if the time is not quite sure, okay, if you're not quite sure of the time that a particular activity is going to take, and in this particular case, a lot of the time, okay, in this kind of questions, they will give you 3 types of timing. Okay, an optimistic time, a most probable time, as well as a pessimistic time. Okay, you've got 3 different timing: optimistic, most probable, and pessimistic. And from these 3 different timing, okay, you can then use to calculate the mean completion time for a particular activity. Okay, the formula to use to calculate the mean completion time is T equals to A plus 4M plus B divided by 6. A being the optimistic completion time, B being the pessimistic completion time, and M being the most likely completion time estimate. Okay, so all these 3 timing will be given to you in the table. So then you just have to use, okay, the formula in order to find out what is the mean completion time. Okay, and we will then draw up a project network just like what you did earlier using the mean completion time. So this is the time that will then be used to draw up your project network. Okay, not your optimistic time, not your pessimistic time, and not your most likely completion time. Okay, you will draw up your project network using your mean completion time. So in this kind of problem, you will then, that means you need to first find out what is the mean completion time before you draw up your network. Okay, and then you will then also be able to calculate the activities completion time variance, okay, which is given in the formula variance equals to B minus A over 6 squared. Okay, so in this 3-time estimate approach, okay, your 3-time optimistic, pessimistic, and most probable, the critical path is determined as if the mean times for the activities were fixed time. Okay, the overall project completion time is assumed to have a normal distribution with mean equal to the sum of the means along the critical path and variance equals the sum of the variances along the critical path. So project completion time, the mean equal to the sum of the means along the critical path. Along the critical path, and the variance of the project completion time is the sum of the variances again along the critical path. Okay, let's very quickly look at an example. The HS Dougherty Company has manufactured industrial vacuum cleaning systems for many years. Recently, a member of the company's new product research team submitted a report suggesting that the company consider manufacturing a cordless vacuum cleaner. Okay, the new product, referred to as PortaVac, could contribute to Dougherty's expansion into the household market. Management hopes that the PortaVac can be manufactured at a reasonable cost and that its portability and no-cord convenience will make it extremely relative to potential customers or potential consumers. Geography management wants to study the feasibility of manufacturing the Portavac product. How long will it take to complete this feasibility study? So this is the activity, the description of the activity and the immediate predecessors. So with this information, you can then sketch your project network. Okay, what are the, so here, remember, we always have to have the start node and the finish node. Okay, and all the activities in between. Okay, and this is the timing that is given. Okay, activity A, optimistically, it will take 4 weeks to complete. Most probably, it will take 5. And at the worst, pessimistically, it will take 12. So first, remember we said in the project network, we are using the mean time to calculate the schedule for the project. So we need to find a mean for activity A. And because here we are dealing with a range, we also need to find a variance for that particular activity because the variance of the critical path needs to be measured as well. So we find out what is the mean time for activity A using the formula A plus 4m plus B equals, mean time for activity A equals to A plus 4m plus B divided by 6. So A for activity, optimistic time for activity A is 4, probable time M is 5, pessimist time is 12. So substitute in 4 times 5 plus 12 divided by 6 equals to 6 weeks. The variance for activity A, substituting into the formula gives you 1.78. Okay. So here in this particular graph, it just shows you, okay, for activity A, optimistically, it will be 4 weeks. Most probable 5 weeks, expected is 6 weeks. Okay, expected here, so that is your mean. So this is called mean, or it can be called as expected time. It is 6 weeks, and pessimistically, it will be 12 weeks. So calculating, okay, the mean or the expected time for each of the activities, okay, gives you this table, this summary table, showing the expected time of all the activities and the variance of all the activities in this particular project. So then, using this expected time, okay, we can then complete our project network. Okay, so remember, in project scheduling based on uncertain activity time, okay, this time here is your expected time or your mean time. Okay, for each of the activities. So again, just like what you did previously, okay, you conduct a forward pass, okay, as well as a backward pass in order for you to complete the network. So from here, we can see, okay, from here we can see that this particular project on Portavac, okay, needs 17 weeks in order to complete the whole project. So which one of these are then the critical activities? So in order to know the critical activities, we need to identify the slack for each one of the activity. So activity A, the slack is 0 minus 0, 6 minus 6 is 0. Activity B, slack for activity B equals to 7. Activity C, what is the slack for activity C? 10 minus 6, that is 4. Activity D is 1. Activity E is 0. Activity F, 15 minus 11 is 4. Activity G, 50 minus 4 is 1. Activity H, 0. J, 0. I, 0. So activities with 0 slack, A. Okay, so your path, A to E to H to I to J and to finish. So hence your critical path is A, E, H, I, and J. So this is your critical. Okay, so you can then, from the information just now, you can also then create a tabular form for it. Okay, so again, as mentioned earlier, the critical path is determined as if the mean times for the activities were fixed time. Overall project completion time is a normal distribution with mean equal to the sum of the means along the critical path and variance equal to the sum of the variances along the critical path. So here we know earlier, our critical path is A, E, H, I, and J with a total completion time of 17 weeks. Okay, and there are variability can lead to a variation in the project completion time. Okay, remember, with the uncertain activity time, we are working with, okay, the expected total completion time. Okay, but then we know that there is a big range, okay, of variation for the particular activities. Okay, and if there are variation, okay, it could actually make the project complete earlier or later. Okay, to look at the variability, first we need to look at what are the paths through the project network. Okay, we know our critical path A, E, H, I, and J, but that is not the only path, right? We have other paths in the network. Okay, we have what other path we have? We have A, C, F, J. Okay, we also have A, D, G, and J. Or we also have one more, which is B, H, I, and J. Okay, so we have 4 different paths through this project network. Okay, as given here, we have 4 different paths. So what we again want to do, okay, is let's first look at the critical path. The expected total time to complete a path, okay, is the sum of all the activities, like what we said earlier. So 6, 3, 4, 2, 2, we have 17 weeks. The variance are the variances on the activities along your critical path, your critical activities. So variance of activity A plus variance activity E plus variance of activity H plus variance of activity I plus variance of activity J. So the variance of your critical path is 2.72 weeks squared. Remember, because variance is squared, so you have 2.72 weeks squared. Okay, we don't usually work with variances generally, so we find the standard deviation. So the standard deviation is the square root of your variance, which is 1.65 weeks. Okay, so this is the total expected time and the variance and the standard deviation for path 1, which is also your critical path. So let's look at calculating the same information for the other path in the network. Okay, so we have the expected completion time for path 1 is 2.72. Activity, okay, is 17 weeks. The standard deviation of path, the variance, okay, is 2.72. The expected time of completion for path 2 is 13 weeks. Okay, with the variance of 2.03. For path 3 and path 4, we calculate the expected time as well as, okay, the standard, this is 2.72. This is not the standard deviation, okay, but here, okay, we are still dealing with the variances. Okay, we are still dealing with the variance, with the square. Okay. As mentioned earlier, okay, the distribution path completion time follows a normal distribution. So if it follows a normal distribution, we can then find what is the probability, okay, that the path of activities can be completed within the time that we specify. Okay, we want to find out what is the probability that it will be completed within, okay, the stipulated time. So let's say, okay, we have the whole project. So we said that the current project, okay, if you look at the critical path, it's going to take 17 weeks. So what is the probability of completing the whole project within 20 weeks, let's say? So you can then, okay, use the normal distribution, find out what is your Z. So remember, Z equals to X minus mu over your standard deviation. Okay, this is from statistics. So this is information from first year, from second year, and now you're going to put all of those into use here, okay, in the 4th semester of your second year. Okay, and once we have this standard value, your Z value, we can then, using the Z table, using the normal distribution table, to find out the probability, okay, of meeting, okay, the deadline of 20 weeks is 0.9659. So there is a 97%, okay, chance or likelihood that you will complete the project within 20 weeks. Okay, so with that, you can also find out what are the Z scores for all the 4 different paths. Okay, and then from there, you can find out what are the probability of meeting a particular deadline that is set by the top management. Okay, so we can see here, okay, that a common computational shortcut, okay, the most basic, or the one that we always find, is the one for the critical path. Okay, because we know that it is the longest time taken for the duration of the project. However, a probability estimate, okay, based only on the critical activities, can be overly optimistic. Okay, so because we are dealing with uncertain activity time, okay, longer than expected time, okay, for completion of activities, okay, with the non-critical activities could actually cause the whole thing to go haywire. Okay, so therefore, what we should do is then to try to find out, okay, what are the probabilities? It will be good practice to find out the probability, okay, for all the different paths. And importantly is that the project manager has to frequently monitor the progress of the project. Okay, especially, okay, the higher the variance is, okay, the project manager should pay more attention, okay, to projects that have the higher variances, because there are potential likelihood, okay, that these projects could actually go haywire because the variance is big. Okay, all right. Before I continue to the third subtopics, okay, let's take 7, 8, 9, 10. Let's take an 8 minutes break. Okay, come back at 10:15. Right, come back at 10:15 and we will go through the third subtopic. Okay? Okay, see you in 8 minutes. Okay, hello. Are you all back? Okay, good. Okay, let's go off to the third one. Okay, which is to consider the time cost trade-off. So when we are determining, okay, the time estimates for the activities, okay, the project manager base their estimates on the amount of resources that is available to them. Okay, resources such as workers or equipments or etc. that they can actually assign to the activities. So the original developers of the critical path, okay, actually provided the project manager with the options, okay, of adding resources, okay, to some of the activities in order to reduce project completion time. Okay, it makes sense, isn't it? When we actually have more resources, okay, let's say a particular activity requires 5 weeks to complete, okay, with 10 people. So if I put in 15 people for the same amount of work, I would expect to take less time, right? So when I provide, when the project manager are given extra resources, okay, it tends to reduce the project completion time. But we also know, okay, that extra resources will definitely increase the project cost. Okay, from earlier, you need to pay 10 people. Now, with the extra resources, you need to pay 15 people. So here, the decision that needs to be made, okay, by the managers is that what are you going to do in such a situation? Okay, I want to reduce the activity time. Okay, but you must take into consideration the additional cost that is involved. So you must actually strike a balance here. Okay, and how do you strike this balance? So as a project manager or the manager, okay, you must make a decision, okay, that involve trading additional project cost for reduced activity times. Okay, so this is where the decision science comes in, the decisions that you have to make. How do you do this trade-off? Okay, so the way to do it, okay, is what we call crashing. Okay, where we try to shorten activity time by adding resources. Okay, but you cannot simply crash activities. Okay, you cannot just simply choose and say, oh, I want to shorten this activity or I want to shorten that activity. No, it doesn't happen that way. You need to determine where you want to crash and how much activity time that you want to crash. Okay, so in order to do that, you must get information, okay, for what is the activity cost, okay, under the normal or expected activity time. What is the time to complete the activity under maximum crushing? Okay, and what is the activity cost under maximum crushing? Okay, what does it mean by maximum crushing? Okay, maximum crushing is the shortest possible activity time. Okay, so a project, okay, even if, okay, let's say just now, a project, an activity is 5 weeks. From 10 people, I put in 15 people, okay, perhaps I will save 1 week. If I put in another 5 people, I might save another week. Okay, if I put in more people also, it will still need that minimum of 3 weeks, regardless of how much, okay, resources I put in. So that is the shortest possible activity time. Okay, 3 is the shortest possible with additional resources given to it. But under normal activity cost, normal activity time, it will take 5 weeks. So you need to know, okay, for each of the activity, what is the maximum time, okay, that is required What is the minimum time? Okay, that means maximum crashing that is required, okay, to complete that particular activity, and what is the activity cost under maximum crashing. Okay, so normal time activity cost, maximum crashing, as well as activity cost under maximum crashing. So let's look at an example here. Okay, this is an example of a tool machine maintenance project that contains 5 different activities. So management has substantial experience, okay, and they can provide you with the expected time for maintenance activities here that has very little variability. Hence, they provide us with the single time estimates for each of these activities. So with this kind of information, we will then able to draw up or sketch out the project network. And once we have a sketch of our project network, then we can use the forward pass and backward pass calculation in order to calculate, okay, our earliest start time, latest start time, earliest finish time, latest finish time, slack, and identify the activities on the critical path. So here, okay, you can go through that, okay, but here given in this table, so activity A, B, and E is on your critical, are your critical activities, so they are your critical path. And the length, okay, for the activities, if we look at the earliest finish time and latest finish time, this is 12 days. Okay, so here we are dealing with days, so this is 12 days. Okay, so next, okay, we want then to calculate, okay, what is the maximum time reduction and what is the cost per unit reduction of this particular project. So in order to calculate that, okay, we can use the formula M of I equals to tau I minus tau prime I. Okay, tau I here is the normal time to complete an activity. And tau prime I here, okay, is the crash time. Okay, and the cost is the cost, okay, maximum crashing cost minus the normal activity cost divided by, okay, the M of I, which is your maximum time reduction. Okay, let's look at how we calculate this. If the normal or expected time for activity A is 7 days at a cost of $500, maximum time under crashing is 4 days at a cost of $800. Okay, so maximum possible reduction time. Okay, normal time is 7, maximum crashing, you need minimum 4 days. So I can potentially crash it for 3 days. That means I can complete it normal time. Normal time, I do it in 7 days, or I can do it in 6 days, or I can do it in 5 days, or I can do it in 4 days. Nothing more than that. Nothing less than that. So I can here crash it for 7 minus 4, which is 3 days. And the cost is, okay, it is under normal time, it is 500. Under crashing time, it is 800. So we want to find out how much is the cost of crashing per day. So here, so we take 800 minus 500 divided by 3 days. So that is $100 a day. So that means now under normal activity time, this cost me $500. Remember, I can crash it for 3 times, okay, 3 days. So if I crash it the first day, okay, from 7 days now becomes 6 days, that means, okay, my cost will go from $500 to $500 plus $100. So now this becomes $600. Okay, so then this is crashing for 1 day. Or I can choose to crash for 2 days. So 7 days now becomes 5 days. And the cost is now 600 plus 100. So this is now $700. So that means now I do it under 2 days of crashing. And so on, I can do it up to 3 days. So reduce it to 4 with a maximum crashing cost of $800. Okay, so it depends how many days you want to crash. That is why it is important. The decision here is this. Remember, I've highlighted to you, you need to determine where you want to crash and how much you want to crash. So you need to know first, okay, before you decide where and how much, okay, you need to have the information available to you. What's the cost now? How much can I crash? What is the cost of crashing? So you need to identify those kind of information, and that is what I'm doing here now. Yep. So crashing days increase, meaning that I'm reducing the time it completes the project. Okay, if I crash 1 day, from 7 days, it will now become 6 days to complete activity A. If I crash another day, if I crash it by 2 days, that means an activity that originally requires 7 days at $500 is now 5 days. I can finish it faster, but the cost is now at $700. Okay, so as the manager, you then need to decide, is this the right decision to make? Okay, and if you decide to crash an activity by only 1.5 days, then it will be 1.5 days plus $100 is $150. Then the results will be 500, which is the original. This is the original activity time, activity cost plus the crashing cost. So now this is your revised activity cost. Okay, so we can also use a graph. If you want to see a graph, the normal operation time is 7 days. The maximum possible crash activity, okay, maximum, I can crash it for 3 days, so maximum is 4. So then this is the kind of like cost in between. So you will need then to find out, okay, what is the maximum reduction time, how much you can crash for each of the activities, and how much is the crash cost per day. Okay, generally this information here, okay, will be given to you. Okay, this information here will be given to you, but you will then need to find out what is the maximum reduction in time as well as the crash cost per day. Okay, so now that you have this information, you will then need to ask, okay, I have this information now, which activity should be crashed? How much should it be crashed? Okay, in order to meet a specific deadline that is set for you, and obviously the target here is to complete the activity within minimum cost. Okay, so we know, okay, why I say we cannot simply crash an activity. Okay, so let's go back to our activity here. Okay, we have got our project network, and from here we can see that A, B, and E, okay, this is our critical path. Okay, we don't have any slack here. Let me just quickly fill this in so I can use this to explain. Okay, so this is 07710. 00770 0077. B is 771010 771010. Activity C is 0167, 0167. Activity D is 6, 7, 9, and 10. And activity E is 10, 10, 12, 12. Okay, so this is our network. Okay, so where do you want to crash? We can see here the first reaction, the first place that you want to crash is on the critical path. Why? Because if I want to crash the critical path, only then I can reduce the time of completion of my project, right? If I were to crash activity C, if I reduce this, okay, if I reduce this slack, if I have to crash it, reduce it by a day, I will only reduce my slack. I will still not make any changes to the time that it takes to complete my project, right? So now, however, now the aim here is to reduce the time it takes to complete your project. So let's say if now I want to reduce this from 12 weeks, now I want to say, can I complete this within 10 weeks? Sorry, 10 days. This is days. Sorry. Can I complete it within 10 days? How can I complete it within 10 days? So in order for you to crash, okay, you will need to crash it 1 day at a time. Okay, 1 day at a time. So here you want to reduce this to 10. You want to reduce the completion time to 10. The best place to start is on your critical path. So that means either activity A or activity B or activity E. So let's look at activity A, B, and E. Okay, here. Activity A, okay, you can reduce it. Okay, so we are looking at activity A, B, and E. Okay, activity A, I can reduce by 3 days. It cost me $100. Activity B, I can reduce it by a day. It cost me $150. Activity E, I can reduce it by a day. It cost me $250. So remember, we want to crash it to meet the new deadline, but at a minimum cost. So the first place you want to look at is which of these 3 activities cost the least? $100, $150, or $250? Then obviously it is $100. Okay, and in this particular example, activity A can be crashed up to 3 days. So remember my deadline, my new deadline, my deadline is from 12 days, I want it to 10 days. So technically speaking, I need to crash 2 days. So in this case, activity D, I can crash 3 days. So what I will then do is to crash activity A. Okay, so I will crash activity A by 2 days, and then it will reduce, okay, to 10 days, the total time needed for the project to 10 days, okay, at a minimum cost. Okay, minimum in the sense that if I compare it to $100, $150, or $250, then it will be the minimum cost is $100. Okay. So let's say now, okay, let's say, yeah. So let's say now this is 1 and this is 3. How will you crash it now? Okay, how will you crash it from 10 days to 2 days? Sorry, from 12 days to 10 days. Okay, we have here, let's see, B, 1A, 1B, B, 3 days just cost $150. No, this is cost per day. Crash cost per day, my dear. Alamak. Yes, so here the correct one is you crash 1 day of activity A that costs you $100, and then you crash 1 day of activity B, it costs you $150. So now your total extra cost from crashing is $250. Okay. Yes, you can choose any activities on the network. Okay, just as long as you can crash it. Okay, and it comes with the minimum cost. Okay, but bearing in mind, okay, here, important here is keep in mind, however, when you crash the current critical activities, other paths may become critical. Okay, so what you will need to do, okay, when you're crashing activity time is to check, okay, the path of your network constantly. Okay, consistently pay attention to which activity you are actually crashing and how it could potentially change, okay, the time of the path within your network. Okay, so if you have a small network, okay, like what we are having here, okay, in this particular network, it is a small network, so we can keep trying. Okay, let's say I crash this, and then you can recalculate the critical path, etc. However, if you have a very big project, as we know, some of the projects are very big, then you will then need a mathematical procedure to actually determine what is the optimal crashing decisions. Okay, there's always software that you can use in order to do that. Okay, but at the moment we are not worried about that here in this course. But here, what we want to look at is really the concept of crashing. Okay. Okay, any questions so far on this time cost trade-off?
Doctor, can I ask a question?
Sure.
If activity A and B reduced by 1 day each, so it also will affect the another path, right? Which is C and D.
It could potentially affect another path, yes.
So the activity C and D also have to reduce the activity time or
so okay, when you do with this, okay, so let's say because A and B is at the top. So now let's say if this is becomes 6. Let's do activity A first. This is now 6. Okay, so I'm just going to delete all this. Okay, let's look at what I mean. Okay, so this is now 6. So activity A is 6. Activity B starts with day 6. Takes 3 days, so this is 9. So activity E, do not know yet. Activity C doesn't change, so this is 0 and 6. So 6 and 3 is 9. So here this is 9 plus 2 is 11. Okay, backward pass. Activity A is 11 minus 2 is 9. So latest finish is 9. 9 minus 3 is 6. 6 comes here. Again, 9 minus 3 is 6. 6 comes here, so now this is 6 and this is 0. So now you have 2 critical paths. Okay, I know this is under the circumstances. So now I have 2 critical paths. Okay, I have used up this $100. So this one I've used up. So next, which activity to crash now that both of them are on a critical path? So I can choose. This is 150, this is 150. So I can choose now to crash activity B or activity D. Okay, so if I choose to go with activity, okay, assuming B, we know what to do. Let's say activity D. So because both of these path is now a critical path. That's why I said earlier, okay, when we crash an activity, we could now potentially change the critical path. So this is what happens here. We have now changed. So now the critical path. Okay, so once crash, I have now 2 critical paths, which is A, B, E, as well as C, D, and E. Okay, crashing of activity D and activity E is now the least, so I can choose either one to crash. So let's say I crash activity D. So now this becomes 2 days. So now I will then have to redo my network. So this is 6 plus 2 is 8. 8 and 9. Okay, so this is 9. This is 2, 11. So it doesn't work. See, if I were to crash activity D, it doesn't change. So in this case, I have to crash 2 activities. I can crash activity D and activity B, or I can see what is activity E. How much does it cost me to crash activity E? Activity E is 250. Okay, instead of me crashing 2 on 2 critical paths, I might as well crash activity E. So now the decision is then not to crash activity D. Now I want to crash activity E. So this was 6 and 9. I don't crash here. So this is 6 and 9. Okay, 9, but instead of 2 days now, this becomes 1 day and this becomes 10. 9, 9, 6, 9, 6. Okay, so when you're actually drawing the path and not by looking at the table, you should see that you should crash activity A and you crash activity E. So this is $100 and this is $250. So it adds to $50. Okay, but however, the original the very original question, okay, you have more time in A. Okay, so you have $100 with 3 days. So in this particular example, okay, it will then be very straightforward that straight away you crash this at $100. Okay, all right, any other question? Okay, if no more question, then that we come to the end of the topic. Okay, so by now, okay, you should understand, okay, the role and the application of how you can use PERT as well as CPM for project scheduling. Okay, how you can define project in terms of activities such that the network can be used to describe the project, compute critical path and the project completion time. Okay, if you have uncertain time, then you should be able, okay, to convert the 3 time given, optimistic, most probable, and pessimistic time into an expected activity time estimates. Okay, and if you are working with these 3, okay, you should also be able to compute the probability of the project being completed on time and, okay, understand the concept and the need for crashing and how to schedule and control project cost if you have to crash activities. So which activity to crash and how much additional cost, okay, that it will generate. Okay, so that's it.